Hello everyone, welcome to our audiovisual understanding tutorial. I'm Yapeng Tian from Department of Computer Science at the University of Rochester. Today in this session, I will talk about audiovisual video understanding. This is the outline of the talk. First, I will give an overview, then I will cover three different tasks: audiovisual event localization, audiovisual video person, and audiovisual video captioning. I will end the talk with posing some challenges in the field. Through the years, we have observed a lot of deep networks that are developed to address video understanding tasks, from classic two-stream network and TSN to recent slow-fast and X3D models. We have obtained impressive results on widely used benchmark datasets, such as UCF-101 and Kinetics. Most of them are working on designing efficient and effective modules and frameworks to model temporal information in videos. However, another modality, audio, synchronized with the visual information, is commonly ignored. However, we know that videos are essential multimodal data, in which both audio and visual content can convey important information that can help us to parse and understand the events or scenes inside the videos. In addition, numerous psychology studies have shown that combining different sensory data is crucial for human perception. So why hearing matters? First, sound indicates in-screen scenes.
The radio is blasting, someone's knocking at the door.
We can see that from either audio and visual content, we can easily know what is happening in the video. Then sound indicates out-screen scenes.
Do the half-court shot.
Oh, you ain't getting over me.
No, I'm giving it to you so you can take the half-court shot.
Oh, okay. Hand it to me.
Kobe!
Oh my god, we could totally play dodgeball.
Only when we listen to sound and watch the video, we can learn that there are two men are playing video game. Furthermore, we do have a lot of free multimodal audiovisual data in YouTube. The goal of audiovisual video understanding is to explore both modalities to understand audio and visual scenes inside the videos. Next, I will talk about audiovisual event localization. The goal of video understanding is to understand various and dynamic scenes and events inside the videos. It's essentially a multimodal problem in which both audio and visual information are helpful. In this work, we take both audio and visual modalities into consideration and explore audiovisual events in videos. What is an audiovisual event? Audiovisual events are synchronized video segments in which the sound sources are visible and their sounds are audible. In the work, we collected an audiovisual event dataset called AV dataset, which contains about 4,000 10-second long videos in 28 categories. With the AV dataset, we pose and try to answer several questions. The first batch question is that the inference jointly outperform inference independently. Intuitively, sound should be useful. For the church bell example, from video frames, it's really hard to learn where is the church bell, but the sound can help us recognize visually noticeable church bell. The second question is, how does results vary under noisy training conditions? The question is interesting because fully labeled data is very expensive. To answer the questions, we introduce an audiovisual event localization task. The goal of the task is to predict event label for each audiovisual segment pair. Each segment pair contains synchronized 1 second long audiovisual content. For this example, we have 5-second video sequence here. The goal will be predict the first 2 seconds are background class and the last 3 seconds are chainsaw events. The problem is challenging because we not only need to know whether an audiovisual segment pair is matched or not, but we need to predict what is the event inside the matched segment pair. To address the task, we use a CNN-RN-based model. We explore the problem in both supervised setting and weakly supervised setting. For supervised audiovisual event recognition, we have segment level labels during training. For weakly supervised setting, we only have the video level label. It means that we only know that there's a chainsaw event inside the video, but we don't know where the chainsaw events along the temporal dimension. To address the problem, we obtain the video level label by average pulling over segment predictions for training. Here are results. We can find that A plus V models are always better than either A models or V models, which can demonstrate that joint audiovisual modeling is helpful. In addition, the weakly supervised models can show pretty good performance compared to the corresponding supervised models, which indicates that audiovisual event recognition, even in a noisy training condition, is still tractable. We have observed that audiovisual integration can have audiovisual event understanding, but how does knowing one modality help model the other modality? To discover the audiovisual interactions, we introduce an audio-guided visual attention mechanism, in which we use the encoded audio information as condition to select the audiovisual related content from the visual modality. We visualize the attention heat maps and find that audio-guided visual attention is able to capture semantic regions of sound sources. Here's one additional question is that whether the attention only captures salient objects or just motions in videos. The answer is no. For the mouse example, when the mouse does not make any sound here, the attention will randomly select certain regions. When it begins to make sounds, the model will only focus on the mouse. So the attention can distinguish audiovisual unrelated regions and only capture sounding objects. Here are more results.
And put more bedding in.
Since we have two different modalities, one important question is how to integrate them. We explore three different filtering strategies: early filtering, late filtering, and decision filtering. The early filtering filters the two different modalities before individual temporal modeling. Late filtering filters them after individual temporal modeling, as shown in the figure. For example, here, given the encoded audio feature and the attended visual feature, we will first use individual temporal models. Here, actually, we use LSTM to do the temporal modeling for individual modalities. Then we will fuse the temporal aggregated features for future prediction. The late filtering, we fuse them before the final softmax layer. In addition, we introduce a dual multimodal network to fuse the two different modalities. With skip connection, it can preserve useful information in the original modality and add complementary information from other modality. We can find that late filtering is always better than early filtering and the decision filtering, which demonstrates that individual temporal modeling is important for audiovisual integration. The reason is that audio and visual are different temporal series. They will have their individual temporal patterns. If we first fuse them, which will lose certain important individual temporal patterns. So the late filtering that first do temporal modeling for each individual modality can have better performance. In addition, our model with late filtering is better than other methods, which can demonstrate the effectiveness of our proposed audiovisual filtering. We already know that audio and visual modalities are related. Here are we are curious about how strong the audiovisual correlation would be. We explore a question that, can we locate the content in one modality, given its observation in other modality? To answer the question, we explore a cross-modality localization task, which has two subtasks, V2A and A2A. For V2A, given visual content V, we want to find a synchronized audio segment A along the long audio sequence. Similarly, for the A2A task, given audio content A, we want to find a synchronized visual segment. We introduce an audio-visual distant learning network to address the problem. During testing, we use sliding window-based method to find the best matches. We use streak metric MIU equal to 1 to evaluate performance. Even with the streak metric, the measures show promising results, which further demonstrate the strong correlations between the two different modalities. In summary, joint modeling of auditory and visual modalities outperform individual modeling for understanding audiovisual events. Even mono sounds can spatially localize sounding objects. Temporal alignment is essential for audiovisual fusion. In our work, we first do temporal modeling with different LSTMs, and then we directly use the fuse feature at each time step for future prediction. But the model did not fully explore audiovisual temporal information. Here, to further improve the model, this paper first keep the same setting, use the different LSTMs to do temporal modeling for each individual modalities, get hidden stats and self stats for visual and audio modalities. And then they fuse the features from the hidden stats and fuse the hidden stats and self stats. Then it will use them as the initial stats for a decoder LSTM. Then they will use the connected audiovisual feature with the initialized hidden stats and self stats for future prediction. In this way, the model can fully explore the audiovisual temporal information. The first two works only considered segment alignment and global co-occurrence in long duration are ignored. For example, here is the long video here. We actually have a lot of co-occurrent audio and visual temporal context. To address the problem, they propose a dual attention matching mechanism. For example, given audio input, first we get the segment level features. It will drop the background class here, get the event relevant features. It means that the model needs to assess the annotations. After that, they will perform self-attention for the event relevant features. Then a mean polling is used to get the global audio feature. With the global audio feature, we can compute the matching scores between this global feature and each visual segment. In this way, we can predict a vector which can represent the event relevance. Similarly, given the visual information, we can extract segment feature, do self-attention, and the mean polling to get a feature vector to find the relevant score over the long audio segments. To use the DIM to address supervised audiovisual event localization task, they decouple the task to subtasks. First, it needs to predict the event category. Then they will recognize background class, background segments. During training, they given the audio and the visual sequence, they first extract the features and do self-attention. Then use the DIM to predict the event relevance scores. After that, they will fuse the audio feature and the visual feature to predict the event category. In this way, it can address audiovisual event localization task. Compared to the present methods, the model achieved a better performance. For cross-modality localization, it's pretty straightforward to use DIM to address the problem. With the DIM, it will produce a relevant score. We can directly use the relevant score as the matching results to address the cross-modality localization. There are also other works that explore audiovisual event localization. If you're interested in the topic, feel free to read the other papers. Next, we'll talk about audiovisual video person. Videos contain various and diverse temporal video events, which are either audible, visible, or both. Here are some examples.
Only has to do it when she has a frisbee or
In the audiovisual event recognition task, it only explores the audiovisual events. However, there are also a lot of other events which are visual only or audio only. These audiovisual examples are ubiquitous, which leads us to some basic questions. What video events are audible, visible, and audio-visible? Where and when are these events inside a video? How can we effectively detect them? To answer the above questions, we pose and try to tackle a fundamental problem, audiovisual video person, that recognizes event categories by into sensory modalities, and meanwhile finds temporal boundaries of when such an event starts and ends. For this example, we not only need to know that there's 3 different events, basketball, speech, and dog, are in the video, but also need to detect the corresponding event boundaries and modality types. However, learning a fully supervised audiovisual video person model requires densely annotated event modality and category labels with corresponding event onsets and offsets, which will make the labeling process extremely expensive and time-consuming. To avoid the tedious labeling, we explore weakly supervised learning for the task, which only requires sparse labeling on the presence or absence of video events. The weak labels are easier to annotate and can be gathered in a large scale from web videos. We collect, look, listen, and parse dataset containing more than 10,000 videos over 25 event categories, with video level labels for training and the second level temporal boundaries associated with modalities and event categories for validation and testing. We only have video level labels for training, but we'll predict precise when the label sets for all video segments during testing, which makes the weakly supervised audiovisual video person be a multi-modal, multi-instance learning problem. Let a video sequence with T audio and visual segment pairs be a bag. Unlike previous audiovisual event recognition that is formulated as a ML problem, where audiovisual segment pair is regarded as an instance. Each audio and the visual segment corresponding visual segment occur at the same time, denoted as 2 individual instances in our problem. So a partial bag containing video events will have at least 1 partial video segment. Meanwhile, at least 1 modality has video events in the partial video segment. During training, we can only assess the bag labels. For example, here we can only know that there's a speech and barking events inside the video. But during inference, we need to predict the event category, the event modality, and event boundaries. The temporal and multimodal uncertainty in the problem makes it very challenging. Here, our baseline model, given the visual features and the audio features, then we can predict the individual event category for each segment here with the instance features. Since we have known the individual labels to train the model, we further do polling over the predict probabilities, get the average of the polled probability, which can be trained use the video level label. In this way, we can train the model with video level label using the cross entropy loss function. But during inference, we can still predict the instant level prediction. The segments in video from different time steps and different modality may have different video events. We propose an attentive ML pooling method to adaptively select the most informative modality and temporal segments for prediction. For example, here we have the temporal attention, give the different importance for different time axes. And also we have the modality attention, audiovisual attention, will give different importances at different time steps for different modality. Our attentive pooling is better than the compared methods. For example, here we compare with the max and min pooling method. The reason is that the max ML pooling only selects the most discriminative segment for each training video, so it cannot make full use of informative audio and visual content. The min pooling does not distinguish the importance of different audiovisual segments and equally aggregates the predictions from each instance, which can obtain good audiovisual event person, but poor individual audio and visual person, since a lot of audio only and visual only events are incorrectly processed audiovisual events. Our attentive ML pooling allows us to assign different weights to audio and visual segments with a video bag for each event category, so that it can adaptively discover useful segments and modalities and achieve better performance than the compared best models. The weakly supervised audiovisual video processing framework only uses less detailed annotations without requiring densely labeled audio and visual events for all segments. This advantage makes this weakly supervised learning framework appealing. However, it usually involves model to only identify a discriminant pattern in the training data, which was also observed in previous weakly supervised ML problem. In our ML problem, the issue becomes even more complicated since there are multiple modalities and different modalities might not contain equally discriminating information. With the weakly supervised learning, the model tends to only use information from the most discriminative modality, but ignore the other modality, which can probably show good video classification performance, but terrible video processing performance on the events from ignored modality and audiovisual events. For example, if the model only mainly use the audio information to predict the video level labels, it will not fully explore the visual information. In this way, it can probably get better performance on video level label prediction, but it will get terrible visual pattern results and audiovisual pattern results. Since the video level label contains all event categories from audio and visual content within the video, to address the problem in our setting, we propose to explicitly use supervision to both modalities with a guided loss. Here are our results. We observe that the model without individual guided learning can show pretty good performance on audio event person, but terrible results on visual person and audiovisual person. The reason is that the model mainly uses information from the audio branch, but the visual branch is not well trained during optimization. In this way, the model will get pretty good, the good person results for audio part, but better results for the visual part and audiovisual part. Then we can see that the guided learning can further improve the results. The reason is that with the guided learning, the model will enforce each branch, the audio branch and visual branch, to learn meaningful representation and predictions. Then we can find that we can get much better visual prediction and audiovisual processing results. But the only guided learning, it will get better performance for the audio person. The reason is that the guided loss will contain only labels, since the video level label contain the whole label sets. For example, here is the speech and the barking here, but we can see that in the visual part, we cannot find the corresponding speech. So the speech is the only audio event. So, but for guided learning, the visual guided loss will still use the speech as a label, since we have no the exact ground truth labels. So the model will use a noise label as the training to do training. So it will get better performance. With combining the weakly supervised learning and guided learning, it will reduce the problem and also preserve the better visual and audiovisual processing results. Natural videos tend to contain continuous and repetitive rather than isolated audio and visual content. In particular, audio or visual events in a video usually redundantly recur multiple times inside the video, both within the same modality as well across different modalities. For example, given the red box here at this second, we have the visual event here. We can find the similar event across the temporal domain. We can find the same event here. Similarly, we can find the temporal synchronized event from the audio modality. Also, the temporal asynchronized event from the audio modality. So how to fully explore the multimodal temporal context? To achieve the effective modeling, we propose a hybrid attention model. It will use both self-attention and cross-model attention to individually model the unimodal information and the cross-model information. We compare to the widely used GRU and transform model. Our model shows better performance. Which can show the effectiveness of our model in handling multimodal contexts. Since there's no present method for audiovisual video person, we design baselines based on weakly supervised temporal action localization, sound event detection, and audiovisual event localization method. Compared to the baselines, our method shows better performance in terms of both second level and the event level metrics. Here are audiovisual video processing results.
Until the job was done. We salute you.
The best model fails to find the helicopter sound, but our method can effectively detect audio event, visual event, and audiovisual events. The best model fails to find the lawnmower sound and obtains incorrect boundary. Next, I will talk about audiovisual video captioning. Given a video sequence, the goal of video captioning is to generate a natural language sentence to describe the video content. It's an essential audiovisual understanding task. With adding the audio information, we can get a more comprehensive description for the video. Encoder-decoder sequence-to-sequence model is widely adopted to address the problem. Given the input video sequence, we can first use the feature extractor to get the visual features. Then we will have the decoder LSTM. For each time step, we use the hidden stat as a condition to attend the visual features to get a context vector to predict the next word. For audiovisual video captioning, we have one additional modality, audio. To incorporate the information, this paper proposed an attention-based multimodal fusion model. It uses soft attention over different temporal steps and modalities to get the temporal context for word prediction. At each time step, it uses the decoder hidden stat as the condition. First, for each time step, for each individual modality, they will produce a set of attention events. For example, the alpha 1 will for modality 1, the alpha 2 will for modality 2. Then with the attention events, we can aggregate the features for each individual modality, get the C1 and the C2 context vectors. Then we can use the hidden stat as attention condition to compute the two weights for the two different modalities. Then we can combine the information from the two different modalities with the weights, get the attended final temporal context, temporal and modality context for the word prediction. Besides the attention method, here this paper proposed a new temporal model, which is a multimodal fusion temporal model. Actually, it's pretty similar to the LSTM. Have the input stat, forget stat, out stat, output stat. So unlike the vanilla LSTM, we can see that it will have multiple forget stat. For example, if we have audio and visual modality, we have two forget states, F1 and F2. The reason is that with the forget stat multiply the context, we can pick the useful information for each input modality. With this multimodal LSTM model, we can accurately select the most informative information from the different modalities and make prediction for each word. However, the previous method can address audiovisual captioning with blindly multimodal fusion. How different modalities associated with each other and the relations between modalities and generative words are unknown. To quantify audiovisual fusion in video captioning, we explore associations between semantic words and audiovisual modalities. In addition, we can manipulate audio and visual relative importance to generate diverse sentences for a single video. In this way, we'll equip audiovisual interpretability and controllability into models. Current method usually explore the RNN-based encoder-decoder sequence-to-sequence architecture. When generating next word, the decoder will use visual information, audio information, first word, and RNN hidden stat. However, the hidden stats contain memorized information from different modalities, and which make the models impossible to disentangle the contribution from individual modalities for predicting the next word. To overcome the problem, we threw away the RNN hidden stats. It means that we will not use RNN decoder and propose a modality interpretable word generation structure. In our model, we have two modality indicators, EV and EA. If EV and EA will indicate how many visual and audio information are selected during word generation respectively. To further achieve controllable effect, we introduced two parameters, alpha A and alpha V, to control importance of audiovisual modalities. During testing, we set in different control values. We can explore different modality compositions using a single model. Here, our full model. With pre-trained CNN to extract audio-visual features, LCM are used to do temporal modeling. With multimodal CNNs to extract high-level visual text and audio text joint embedding. Modality via aggregation with audio-visual controller will fuse audio-visual information. Sentence generator will produce words from aggregated audio-visual features. With visual text MMCNN as an example, with visual feature V and audio and the word embedding E as the input, we can construct a 3D visual text tensor and feed it into 2D CNN network. The MSCNN is a language model, so we need to make it auto-regressive. Therefore, masked convolution kernels are used. For this example, this 3x3 kernel. When we predict the next word is, for example, here, it can only assess the start word and the previous word. It cannot assess the future word. To achieve the goal, we can mask the kernels, set the kernel weights at 0 for the right-hand side positions. In this way, when predicting the word is, the words after the word main in the text sequence will not be exploited. For audio text and visual text joint embedding, with MLP to aggregate features and then use softmax to output a set of weights. The weights will indicate importance for each features. We define activation energy to measure modality importance. For example, here we have visual activation energy EV and audio activation energy EA. When the generated word is a noun or verb, if EV is larger than EA, visual content is more important for generating the word. If EV is smaller than EA, the word is more related to the auditory modality. We introduce a controller alpha to generate two parameters alpha A and alpha V to manipulate the audio and visual waves for audiovisual controllable video captioning. Setting controller to different values during inference, it will assign different importance to both audio and visual modalities, and our model can generate diverse descriptions. Here is the formula for the two parameters. When alpha is equal to 0.5, alpha A and alpha V are equal to 1. It means that the both modalities are equally selected and used in our model. If alpha is smaller than 0.5, alpha A is equal to 1, but the alpha V is in 0 to 1. Then the visual modality is penalized. Otherwise, audio modality is penalized. When alpha equal to 1, alpha A will be equal to 0 and alpha V equal to 1. But during training, alpha V and alpha A are equal to 1. That means that the audio text MSN branch may also make contributions to language modeling during training. We cannot ensure that the visual text MSN learns an individual good language model, which will lead to inaccurate sentence generation during testing. To overcome the issue, we propose to use random control alpha to train the model for enforcing the training and testing to be consistent. In this way, the network can randomly sample different alpha to penalize audio or visual modality, which makes the model be able to explore the associations between words and individual modalities, and discover corresponding events from audio or visual modality. With the competing, both audio text and visual text MSNs will learn good language model. Here are our results.
And the sun will always shine for you.
Do the half court shot.
Oh, you ain't getting over me.
No, I'm giving it to you so you can take the half court shot.
Oh, okay. Hand it to me.
Kobe!
Oh my god, we could totally play dodgeball.
So the model can find that the man is from the audio.
Once you find them, I've looked around enough to know that you're the one I want to go through.
Naggisa ng bawang sa butter. Binuhusan ng espesyal na soup stock. Inilagay ang alimango. Ini-stir fry ang noodles. Pinakuluan hanggang nanuot ang sarsa na may sahog na mushroom, red pepper, coriander o wansoy at leeks.
We can see that our single model with setting different controller values, it can generate different sentences, which can be audio biased, visual biased, or audio-visual descriptions. Take a look at the controllable results. We can find that with a single model, it can generate diverse captions. As expected, when alpha is smaller than 0.5, the model tends to produce more audio-related sentences. When alpha is larger than 0.5, it tends to generate more visual-related sentences. When it's equal to 0.5, it may be biased to one modality or make comparison descriptions. To investigate the alpha, we compare results of different alpha on MSR VTT dataset. With the result, we can find that combining information from both audio and visual information can show better results than individual modality. Visual information is more important than audio information on the MSR VTT dataset. static shrinkage importance of audio feature. For example, here the alpha is 0.6, which means that it's slightly more visual information. We can find that it actually can show better performance than the other alpha, which can further support that the MISR VTT dataset is a vision-oriented dataset with a bias to visual modality. We further compare our method with DAFR method. We can see that with and without random controller training, the two models actually show comparable performance when we use fixed alpha. When we compare our method with others, it's not better than the recent method, even without using audio. So whether audio does not matter and it's not important for the problem, the answer is no. Actually, I have shown that we need to use different alpha for different videos for getting the best sentences. So we need dynamic alpha during testing. To demonstrate it, we use the first three metrics to help us make selections for generated sentence for each video. We obtain the three oracle results. Then we can see that compared to the best non-IRO method, our model can show significant relative improvements. To demonstrate it, we can compare a recent CVC GFN and with the dense VID caption method. We can see that the performance is only slightly improved over the 3 years. But when we compare the proposed oracle methods and the other methods, we can see that with the dynamic audio-visual integration, our model can show significant improvements. So the audio indeed matters in the problem. We need to make audio-visual integration be dynamic in our video understanding task. Next, I will give some open problems. I have shown that we can use the audiovisual data in videos to do audiovisual event recognition, audiovisual video processing, and audiovisual video captioning. Furthermore, we can also use the audio feature as additional bonus to address other vision tasks. So, but there's still some challenging problems and never extracted in existing literature. The first one is how to utilize daily undreamed YouTube videos. Previous work usually use collected dreamed videos or even image and audio clips pairs, but it never used the undreamed long YouTube videos. So, but for our free YouTube videos, they are usually undreamed and very long. So how to use this information for to make meaningful video understanding, it will be an interesting problem. Next will be, can we learn audiovisual association and integration within dynamic audiovisual scenes from undreamed videos? Reasoning on dynamic audiovisual events in undreamed videos have not been explored and solved by our research committee. We know that there are audio-visual and audiovisual events inside the video, and they will be dynamic over time. If we build a graph, it will be a dynamic audiovisual temporal graph. It will be very interesting if we can enforce reasoning over the model to address certain high-level understanding tasks. In addition, how to build a joint audiovisual process system to have visually and hearing impaired people. So for visually and or hearing impaired people, they have no certain senses and they cannot fully perceive the world using hearing and sight. But we indeed can build certain perception systems, have them to build a comprehensive understanding over the world. It's very interesting to improve the accessibility for these people. That's it. Thank you.